Noon. It's 10 minutes after, so I think we'd like to get started. So for those of you still getting your lunches, just grab them quickly and be seated so that we can get started and have more time for the speaker. So my name is Gaiman Yi. I'm the Technical Director of the I4 Energy Center, and welcome to today's I4 Energy Seminar. I want to also welcome those that are viewing our seminar today on the internet. Today's speaker is Bryan Jenkins. He is a professor of biological and agricultural engineering at UC Davis, and he's also the director of the UC Davis Energy Institute. Professor Jenkins teaches and conducts research in the areas of energy and power with emphasis on biomass and other renewable resources. He has more than 30 years experience working in the area of biomass thermochemical conversion, including combustion, gasification, pyrolysis, and his research also includes analysis and optimization of energy systems. Professor Jenkins holds degrees in agricultural engineering, a BS from University of Maryland, and MS and PhD from UC Davis. Let's welcome Professor Jenkins.
Yeah, thank you. It's a pleasure to be here this afternoon. Thanks, Gaiman, for the invitation, and thanks to you all. Also to those of you who are observing remotely, greetings from UC Davis. And so my talk today is going to discuss some of the work we've been doing in large-scale systems modeling around renewable energy development. Particularly, it will focus on the work in bioenergy that we've done in terms of developing a regional and national scale model around biorefinery siting and infrastructure development. And I'm here presenting this information, but let me point out to you that there's a large number of people who are involved in this, and some in particular, the postdocs and the graduate students who make up the intellectual core of all of this activity and who really represent the knowledge base behind this development. And it is my pleasure to present on their behalf this information to you. And I'll try to get through this fairly quickly with enough time for some questions at the end, hopefully. So let me go through. And before I do begin, let me tell you a little bit about where I come from at Davis. We have a number of energy programs and have had a lot of activity, research activity, educational activity, outreach activity in energy for a long time. These have been formalized in various ways. We have a number of major thrusts in energy at UC Davis, including in energy efficiency. You may know we have an energy efficiency center there. They have, as part of that center, they have the California Lighting Technology Center. They have the Western Cooling Energy Efficiency Center, and there's a new center associated with water and energy efficiency relationships. And we also have a lot of activity in renewable energy. Some of you perhaps have been working with us over the years in some of these areas. We do operate for the state of California under California Energy Commission sponsorship and some other sponsorships. The California Renewable Energy Center used to be called the Collaborative. It's now the Center, but it has a number of programs within it, within each of the main renewable energy resource categories, including an integration program which looks at how do we integrate renewable energy systems across the larger energy sector. We have various programs in bioenergy and photosynthesis, artificial photosynthesis. We also have an agreement with Chevron Corporation on biofuels development, and then we're also a partner in the Joint Bioenergy Institute, which is headquartered here in Emeryville. The Institute of Transportation Studies, which is an institute that the Energy Institute, partners with quite a bit, has programs in sustainable transportation energy. We have the Sustainable Transportation Energy Pathways program, in fact, which does a lot of work on renewable and other sustainable energy in transportation systems. There's a plug-in hybrid and electric vehicle center at Davis, which works a lot on electric vehicles and plug-ins, of course, and has been doing quite a bit of work in public response around these types of vehicles. And we also have work in the urban land use. Also, we're trying to build the educational program at Davis in energy. We have a proposal for an energy graduate group, which would offer MS and PhD degrees in 2 tracks, energy science and technology and energy management and policy. So that's before the system-wide academic senate for review right now, and hopefully we'll have that off the ground in a year or so. We also have various international programs. We have the D-Lab program, which is a design lab, which does a lot of work on what we used to call appropriate energy development but working in developing nations, but now extending that. We have a number of collaborations in Europe right now, for example, working with the Danes and others on these types of programs. And then the College of Engineering has recently instituted several minors for the undergraduate program in energy science and technology, energy policy, and energy efficiency. And then we also have a sustainability in the built environment program as well. And then there are various other activities here in terms of graduate education. We have an IGERT through NSF, the National Science Foundation, working in biotechnology and bioenergy. And then we have a resource program, which actually is NSF funded to put graduate students in K through 12 grades, working with teachers there to develop energy curricula at the very young grade levels, and hoping to build capacity for the future there as well. So this is a little bit about where I come from. And related to that then is programs that we have in systems modeling. And the program that I'll talk to you today about deals with bioenergy systems modeling and trying to understand more of the policy, the impacts of policies and development in this area. And so I'll show you the structure and some of the results of this model and talk a little bit about where we want to go with it. Of course, this whole issue of infrastructure modeling or large systems modeling, and you have quite a bit of this activity going on here as well at Berkeley, of course, deals with this basic need, this recognized need for better and more comprehensive modeling in this whole area, because as we really design and build new industries, we need to have much better understanding of what their overall sustainability impacts will be and how we can shape the policies to better influence the design, the sustainable design of these systems. And so this basic need for a better understanding of the spatial distributions has been well acknowledged. We also, of course, have the issues around temporal development of these industries. And so the model I show you today is not quite there, but we will be looking to add in the uncertainty elements and the temporal development of the industry as we move forward. Of course, we have lots of policies that influence sustainable development in the state and in the nation and around the world. You're well aware, I suspect, of the policies around and the desires to get to a very low carbon future in California. We have AB 32, of course, but beyond that, we have this basic desire to get to something like 80% below 1990 levels for our greenhouse gas emissions. And in my case, as being a citizen of the state of California, that means I would have to go from something like, well, our current 13 metric tons of carbon per year down to something around 1 ton of carbon. And so we're really looking at an essential decarbonization of the energy sector out through 2050. And I don't think I'm reducing my CO2 at something like 1/4 of a metric ton per second here, but I hope you are. We also have, of course, policies around renewable fuel development. This is the federal policy, the RFS put in place under the federal legislation in 2007, which calls for the development of 36 billion gallons per year of biofuel. And you can see part of that is coming from corn ethanol. There's a limit, however, on how much can come from corn, and the rest of it is basically coming from cellulosic feedstocks or other advanced feedstocks. Now, you can also see that we have various targets out here. This graph starts back here. I don't know if you can read it at about 2006 with various targets that move out here. I guess we're supposed to be out here at around 15, a little over 15 billion gallons overall. Most of that, of course, being corn ethanol. But there's also some demand here for fuels coming from other sources. We have failed to meet these requirements under the standard, and you can see that the EPA has had to reduce the requirements in the previous years here, and probably will again in the coming few years. We also this actually is based on a lot of analysis around how much resource we have in the country for producing biofuels. You've probably seen something around about a billion-ton study. The billion-ton study, published initially in 2005, has recently been revised. And basically what it did was to find that the United States had resources in the amount of something around 1 billion tons, actually 1.3 billion tons, that were considered to be sustainably available from agriculture and forestry for the purposes of producing biofuels and other bioenergy or other products. And these reports are available on the web, of course, and the latest one is out, and you can evaluate these. What we've done with our modeling is try to understand these analyses, do independent assessments of these these resources and then better understand, or try to better understand how the industry might build out around these resources. We also don't really understand very well what are the best uses for these resources. So the resources have many uses. We can make electricity out of biomass, for example. We can make biofuels out of it. We may be able to drive different number of miles on each ton of biomass. You can see here some comparisons about different fuels that we might produce compared to electricity and how far we might go with these. Of course, there's a lot of issues that accompany these in terms of the overall feasibility of the system, the economic feasibility of the system, the sustainability of the system. And so we don't even have a good understanding yet as to how we should best be using these resources. And so again, the modeling that we're engaged with is an attempt to try to better understand these types of issues. So let me tell you a little bit about the geospatial modeling system that we've been developing around bioenergy, with a goal really to develop biomass supply chain optimization. In this case, for the United States is what I'll talk to you today about, but we've also done it for California, we've done it for New York, we've done it for the western region of the United States. We've tried to focus in on different levels, and we're also engaged in a project right now looking at fuels production from hardwoods in the Pacific Northwest under a grant with USDA. And so we've had various supporters of this effort here, the Western Governors Association, the U.S. Department of Energy, the United States Department of Agriculture, California Energy Commission, and others have participated in all of this development. And so let me tell you a little bit more about the background for this. So the model that we have here, this bioenergy systems model, this geospatial model, includes both a geographic information systems analysis of the resources and infrastructure and fuel delivery system in the United States, and couples that with an optimization model. It's a mixed energy linear optimization model. And the optimization model can use different objective functions. And of course, those of you that are familiar with operations research and optimization know that in order to do the optimization, you need some kind of objective function. Now, the objective function that we're using with the modeling effort, that the large geospatial modeling effort, is around a maximum profit objective for the industry. I'll just show you a simple example here as a background introduction to the optimization effort, which looks at nothing more than the minimum cost of energy from a facility that might use biomass. Could be an electric generation facility, could be a fuels facility, could be anything you want it to be. In this case, we have some, if I go back there, we have some basic objective function in which we want to minimize the cost of energy out of the facility, and that cost will be comprised of three components: the capital cost, the operating cost, and the feedstock cost. And so where we're using biomass as a resource for these facilities, then we need to procure that feedstock, and so there's a cost of doing that. Now, you know that biomass is a distributed resource. It's grown around the facility. It may have to come from quite some distance away. The farther away we have to go, the higher the transportation costs associated with that. And of course, the larger the facility, the more resource that we need to bring into the facility in order to provide for the capacity of that facility. And so there's a supply cost for that facility, which is a function of the size of the facility as well. And so we can define other factors in the optimization that we need to consider. For example, in the capital cost, we look at the economies of scale associated with different facilities and technologies. And these are issues that we need to better understand, because we don't always completely understand the economies of scale that go with something like a power generation facility or a biofuels production facility, as we go from, say, a few million gallons a year on a biofuel production facility to hundreds of millions of gallons per year. And so we can represent an economy of scale in some simple ways here. For example, this equation over here on the left simply relates the cost of a plant to the capital cost of a reference plant, for which we know, for this size of reference plant, we know the capital cost of that, and then we project on the basis of the size of the plant we want to install on the basis of this scale factor, what the capital cost might be for that plant. So it's a very simple relationship. If we take this capital cost and divide it by the size of the facility, we get this factor K, in which we have the capital cost per unit capacity, and then the economy of scale goes as that equation on the right, as you can see. So we can rewrite, on some simple example, we can rewrite our objective function here, and I'll show you just real quickly here something that we've analyzed on really for a power plant basis, in which we take all of these the capital costs, the operating costs, the feedstock cost components, we accumulate all of these, into this cost function, cost of energy function. It looks like this, but basically it has some coefficients here which depend on the size of the facility and the scale factor. And I won't go through all the rest of those. They're not really relevant here. But we can do a very simple optimization here. We can try to maximize or minimize the function. In this case, we want to minimize the cost of energy out of the facility. And so all we have to do here is take the derivative of that cost of energy with respect to the size of the facility, set that equal to 0, and this is what we get for the optimal size. So on an analytical basis, we can actually calculate what the optimal size of the facility should be. And you can see that this includes a couple of those coefficients, the A and B coefficients, and it includes the scale factor, both there and there. But the C factor has disappeared, of course, from this. And what you get when you solve for this and plot out, if you plot out the the cost of energy for this facility under a certain set of assumptions, so you can see over here on the left of this slide a lot of different assumptions that go into the power plant, and what you find is that you have a total cost curve for the power plant that looks something like this, and it has a minimum out here, which is actually computed by that previous equation. And what you can see in this particular case, if you look down here, under these assumptions, which seem to be fairly reasonable assumptions based on the biomass power industry power generation industry that's been built out so far, is that we actually have an optimum that's out here at about 1,250 megawatts. Now, I don't know how many of you know the size of the facilities in California and elsewhere around the United States, but they're not 1,250 megawatts. I don't think we have any facilities of that size anywhere in the world burning biomass by itself. So this is quite a large optimum and suggests that maybe we're actually well aware from the optimum size, and we have various reasons for that. One, in California, if we get above 50 megawatts, we become subject to licensing review by the California Energy Commission, so you won't find many, I don't think you'll find any biomass power plants currently operating that are above 49.9 megawatts net to the grid, and so they stay below that. FERC has a limit at 80 megawatts. But nonetheless, you can question, this is all based on an assumption around this scale factor. And if you can see this over here, this analysis is done with a scale factor about 0.91. Now, what does that mean? It means that there's not really all that much economy of scale in the capital cost function for this type of facility. Now, we can make different assumptions about this, of course, and you can see then what happens to the optimal size of a facility under different assumptions for the scale factor. So here's our S value. If you look up here, this is the optimal size of the facility. So this is just so many megawatts. Here's the one that we just solved. It's about 1,250 megawatts at this S value above 0.9. And then you can see as you plot this, you can actually get a maximum in the optimal capacity of the facility, somewhere above 2,000 megawatts there, close to 2,300 megawatts. That's a pretty large facility for biomass. And then you can see the characteristic behavior of this, and so this is all subject to the sensitivity in that scale factor. Now, do we believe then? You can also see the sensitivity here. You can see in this region between about 0.8 and 1 scale factor that there's a lot of sensitivity to the solution in that region. And then you can do other sensitivity analysis, which I won't go through here, except to point out that there's quite some interesting behavior in these types. Even this very simple analytical solution has some very interesting behavior. But what happens to the risk associated with the facility and the scale factor that as the facility size becomes quite large? Particularly when we're talking about biomass facilities, as the size becomes very large, we have a lot of risk associated with simply getting the feedstock into the facility. Does that change the scale factor? Well, in general, it does. And if we look at large coal and nuclear facilities, we find that they typically also have scale factors well above 0.9. If you've done work in the chemical process industry, you know that the scale factor is typically around 0.6. And so that you can look back on the sensitivity graph I just showed you and see how that affects it. But if we get up towards 1, then essentially we don't have any economy of scale in the system. But we might suggest, however, that for some systems, particularly as they get larger, that the scale factor tends to change. And so this assumption of constant scale factor that is sometimes made may introduce results that are, or may produce results that are not entirely consistent with the actual practice that we're interested in. And in particular, if we use an assumption here, let me just back up. Suppose, for example, that we were at very small scales if we said we had a scale factor down around 0.6, but that as we got to very large, we got scale factors up above 0.9, then this is the type of behavior that we would see. If we have a constant scale factor, the one I showed you before, that's what the capital cost per unit capacity would look like, this green curve here. But if we make some assumption about the variability of the scale factor, then we get this kind of behavior. And you can see that the cost per unit capital, or the capital cost per unit production goes up quite substantially as we get to small scales. And actually, we do see some of this behavior in some of the types of technologies that we're working with today. And the question is, with biomass, which is a distributed resource, how might we adapt these technologies so as to reduce these high costs associated with them at small scales? And we'd like to have much smaller scale facilities. And there are other issues that come into this, of course. We can write an equation for this, of course. In this case, I can't solve this directly, so we'll do it by some kind of numerical method like a root finding technique. And what we find then is that we have a different optimum that comes out of this type of analysis, where before we had, under a constant scaling factor, we had some optimum at around 1,252 megawatts, and the assumption, this equation that I invoked for the scale factor dependence on the size of the facility, you can see that this optimizes at some different level, and in this case about 305 megawatts, which is still quite large for any of the facilities that we have in California or elsewhere in the United States. But it's getting down into this range of perhaps better feasibility for the resource distributions that we have. So with this as a background, just as a general background in the optimization area, let me talk now about how we expand this, because these issues come into all of our considerations around facilities, but as we build systems and we build industries, there are a lot more other considerations that need to come in. This analytical approach is perhaps quite useful for individual facilities, but it's not necessarily the best approach and doesn't handle a lot of the issues that come into when we try to integrate across a very large scale. And so in this case, we've tried to build a biomass supply chain or biofuel, bioenergy supply chain model in which we look from the field all the way from the production of the biomass through the transportation network that gets the feedstock into our biorefinery or our process facility and then gets finished product out into final demand. We can also couple this with other systems. For example, if we're running a biorefinery and when we want to also supply feedstock from the biorefinery, either intermediates or raw feedstock to say a power plant that would couple with that, or also supply electricity to the grid, we can model these types of systems as well. So the basic modeling approach that we use here is that we will define some kind of scenario similar to what I showed you before with that power plant optimization. We have to create a set of assumptions that we can use for the industry. Once we create that scenario definition, we can then do our spatial data analysis. We couple that then with our cost, our techno-economic modeling for the conversion facilities, and then we take the output from that conversion facility model and we put that into our infrastructure model for delivery of the finished product out into the market. And so we have spatially explicit resource assessment. That means we have GIS modeling for the biomass resources, and I'll show you a little bit about that in just a minute. We have a transportation cost model. There's a network model for the transportation system. Our fuel transmission cost model, similar infrastructure model. And we have a spatial model for the fuel demand, and then we also have a local fuel distribution model that all of these coupled within the spatial data analysis. These feed into the supply chain optimization model, which is, again, this mixed energy linear optimization model currently running in GAMS. And then we have, coupled with that, an emissions model, so we can, for example, look at the carbon impacts associated with the system that's built out under this scenario definition. And of course, as we change these definitions, then we can realize different outcomes associated with different policies, for example, or different ways of designing the system. And then, of course, we get out of this, we can develop a supply curve for the biofuel, for example, out of the system, which tells us how much fuel we might produce at a particular price level. And, of course, we can then map all of these results and get some idea of where the system or where the industry might build out. So we've considered a number of feedstocks in the model. You can see them here: forest biomass, ag residues, corn grain. We've looked at lipids of various types, energy crops, of course, and also urban resources for biomass feedstocks. The GIS system builds various maps of all of these. So we try to characterize the production levels across the United States in this particular example. We also have to consider what part of this might be considered renewable. For example, if we look at forest resources, this is coming from the definition in federal statute. If we look at forest, for example, slash and pre-commercial thinning, so these are forest materials coming off forest lands that are from non-federal forest lands. So if you're on federal forest lands, these same biomass materials are not considered to be renewable. So if we're trying to define a renewable biofuel, we have to take consideration of these issues that appear in the legislation. Okay. Now we've run through a number of definitions, scenario definitions. I won't go through this in detail. There are lots of assumptions associated with this. Essentially, what we've done is to define a couple of cases in which we have a baseline, which is based on a certain set of assumptions of what we think might be more of the average for the industry as it builds out. We also have a high feedstock case in which we have more feedstock available to the system, and we have a low feedstock case. So we've tried to bracket where we think the industry might be able to tap into these resources and build out capacity. If we look at the agricultural residues, you can see a little bit here about the mapping. If we look at, and we have different bases again for this, but this is basically a low case here, and this is a high ag residues case, and you can see the difference here between the assumptions and how they build out. You can see there's a lot of biomass and agricultural residue in the Midwest, particularly in the Corn Belt, for the resources that we're considering within the model. And then as we change the price for that biomass, going from $50 per ton up to $100 and up to $150 per ton, you can see that the supply increases quite a bit, as you might suspect it would. Same thing for the forest residues as we go from our baseline forest, which looks at the renewable forest materials, and then a high case here, which also includes the federal land biomass. We get differences in the supply there. We also consider pulpwood because as biomass becomes valuable enough, as the feedstock becomes high enough in price, there's probably, the pulpwood market, instead of going to paper or other products, might go to energy. And so we've also included some capacity in that regard. We've looked at energy crops. This model is fairly simple at present. It looks principally at switchgrass as a feedstock being developed under various high baseline and low scenarios as well. You're looking at the baseline and high scenarios here for energy crops. And out of this then, if you look at the resources that the model projects, under this low estimate, you can see that we're ranging anywhere around 300 million dry tons of biomass that would be produced under this scenario. Under the baseline scenario, this gets up into the range above 500 million tons, and then under the high estimate, we're up in the range of about 700 million tons of biomass available. Now you can compare this with what the billion-ton study produced, and those of you who've read the billion-ton study, or at least looked at the title page, know that it produces something above 1 billion tons. And so we've also used the revision of the billion-ton study, the federal billion-ton study, as a scenario on this, and so we've also analyzed that case as well. But for this assessment here that we've done based on the resources we've analyzed, then we get the highest estimate we get up to here is about 700 million tons of biomass available. On top of that resource base, then we apply our transportation network model. And so this model includes three main modes of transportation. So it's roadways with trucks mostly, railway, and marine. We do include marine resources. And then we look at a number of different conversion technologies. So we look at lignocellulosic ethanol production via biochemical techniques. We look at production of diesel substitutes by Fischer-Tropsch chemical catalytic techniques from gasification of biomass. We also look at upgrading of oils to hydrocarbons. And we also look at the fatty acid methyl esters, the standard biodiesel that we produce from lipids. Okay? So we have a number of these. The costs associated with these is, of course, subject to a great deal of uncertainty. Now, we've done quite a bit of examination of the literature around this and various projections of the cost. Here you can see for cellulosic ethanol that most of them come into this range here. This is a 50 million gallon per year capacity for these systems. You can see there's quite a range in the estimates for the cost of ethanol out of those facilities. Okay? We do have some information on economies of scale. We've used this information in combination with other scale information, for example, the Fischer-Tropsch diesel production technologies, which again, we've looked at the literature and tried to understand better what the costs of this might be. You can see the costs associated with different assessments here, and again, In this case, we're looking at a little bit different scale factor, or a unit here. This is in megawatt thermal here, 500 megawatt thermal there for these production facilities. But again, you can see something about the economies of scale that are projected with these types of facilities. And then this graph shows you optimistic, pessimistic, and baseline cost factors that we've associated with the different conversion technologies, in particular here, the cellulosic ethanol and the Fischer-Tropsch diesel production, and comparing those, where you can see the baseline Fischer-Tropsch diesel here actually sits a little bit below the baseline cellulosic ethanol in terms of cost, and then we also include an optimistic cost estimate for ethanol from the cellulosic or the biochemical production facilities. And we compare these in the model results to see what impact they have on the supply curve. Also, there is a layer for fuel demand. And so this is the fuel that we use for driving in the United States. And it shows you how the demand varies across the country. It also shows you the locations of the fuel terminals. And we use these sites as delivery points for the fuel or the product coming out of the biorefinery. And so we look at the location of those and how they impact the cost structure for fuel coming from the biorefineries. The model structure essentially is this. We have set various price levels, and at each price level then we analyze what the cost of fuel delivered into the terminal would be, and then the profit associated with that for the industry overall. And so we have to consider the biomass type, so these are the different feedstocks that are available. We have to consider where they are geographically. Now we look at the potential biorefinery sites and the delivery of those feedstocks into the biorefinery sites. And then, of course, the delivery of the fuel coming from those refinery sites into the fuel terminals. Okay, so that's the current structure for the model. And I'll show you then the equation set for this. So we look at the profit coming from the industry here, which of course is based on the total production and the price associated with that fuel. Minus, of course, the cost. And the cost is dependent on the procurement cost for the biomass is dependent on the transportation cost for the biomass and the conversion cost for the biomass. And then this optimization is subject to various constraints. You can see, of course, read down through here that we, of course, can't exceed the maximum resource supply and the use of resource by the model, so that's a constraint. And we have many other constraints that go into this, including we can look at the case of a blend wall, where we may be constrained, for example, by the amount of ethanol that we can blend into gasoline. So the 10% blend wall, we can't necessarily use as much ethanol in the United States as we might be able to produce, for example. So we can consider that in the model. Okay, so this is a result of this analysis, this model analysis, under the various scenarios that I showed you earlier in that table. This, basically the high, low, and baseline scenarios. So the black line here is the baseline. What you can see is that these estimates vary quite a bit, of course, as you look over the different assumptions in these. This band, the width of this band here is basically the uncertainty under those assumptions. And we can see that if we want to try to meet this is the RFS2, the Renewable Fuel Standard for the United States, the 2022 mandate for biofuels production. This graph down here, this is not at 36, as you might expect, because that's a biofuel basis, but this is in millions of gallons of gasoline equivalent per year. So because of the different energy contents of the fuels, and this comes out down here at around 24, 25 thousand million or billion gallons per year. And you can see that this comes in somewhere around our marginal cost for the biofuel at a little above $3 per gallon gasoline equivalent. And so you can see over here that at about 3 to 4 gallons per gallons of gasoline equivalent, $3 to $4 per gallons of gasoline equivalent, sorry, that we have different resources that go into the production of that quantity of fuel. Something like 2 to 10% coming from waste, and 0 to 7% from energy crops and pulpwood, and then 1 to 5.5% from corn, and with an overall supply of potentially 6.5 to 22% of the total light-duty vehicle fuel demand. And in this case, this is based on the 2018 resource supply scenario because that's the data that we have available. We don't have a supply scenario or a supply estimate for 2022 yet. And so this model is based on the 2018 supply estimate. Okay. We can also look at, for that supply curve, where the biofuel comes from. For example, these orange bars here, these are all corn ethanol. And then you can look, this is coming from the urban waste conversion to Fischer-Tropsch diesel, and so on. We can look at where all of this comes from, and again, this is the baseline supply curve for the biofuel production from these resources. Here's what the industry might look like under the baseline scenario, where we have, of course, a lot of production in the Midwest here out of the Corn Belt, production from mostly urban, and this colored differentiation down here is for urban resources along the California. And then we have forest resources up in this region, and of course forest resources in the southeast region will be producing in this region. So these biorefinery locations have all been optimally sited under this model. We can also look at how far the resource has to go to reach the biorefinery. There's sort of a conventional wisdom out there that you can't transport biomass economically more than about 50 miles from the facility. But what we find in the model is that under the optimizations, that you can actually afford to transport it a lot more than that, and based on the infrastructure that's available. And so this shows you a bit of the distribution here in terms of the biorefinery size, and then this curve shows you about how far we have to travel to get the resource into the facility. And at 50% of the cumulative biomass, so 50% of the biomass going into the industry, this is at about 65, 70 miles transport distance associated with that. We can also look at various sensitivities, for example, to the types of resources that we have available and what assumptions we've made. So these are all based on different assumptions about how much resource is available. So we have the high energy crop, the low energy crop, and so on. The baseline model is here. And so depending on, of course, for our high assumptions here, we can get much beyond what the baseline model shows for total fuel production from the industry with those resources. We also have different technologies, and we can look at the differences there based on the technologies. You'll see the optimistic and pessimistic technology assumptions with the lignocellulosic ethanol conversion, the biochemical processes, in addition to the Fischer-Tropsch technologies. I also have cases in which we look at ethanol from biochemical being the dominant technology in the system, so a different scenario analysis there. And we can also look at what happens as we increase the number or the amount of fuel going into the fuel flexible vehicles, or the E85 consumption. So all of these can be considered as well. So this is what an industry might look like to meet the renewable fuel standard. And again, it looks very similar to what you saw before. We've identified under these assumptions these categories here in which we have conventional biodiesel, we have dry mill technology for corn ethanol, wet mill technology, and we also have the Fischer-Tropsch diesel. And that's associated a lot with, of course, the lignocellulosic resources. To achieve this mandate, then, we would need something like 200 to 250 commercial-scale cellulosic conversion facilities, and this is at a capital cost of somewhere between $100 and $360 billion. The corn ethanol and the cellulosic biofuels from the urban sources and the forest residues are really the low-cost pathways under this assumption. Okay, so the energy crops are not contributing a substantial amount in this case. We can also look at the effects on carbon. In particular, we can look at the cost effectiveness for carbon abatement in the system based on these results. And so in this particular case, we're looking at different oil prices. So this is at $45 per barrel oil price. This is at $95 per barrel, and this gets up to $165 per barrel. You can see that there's quite a bit of greenhouse gas abatement that can occur under these, as we increase the oil price. As we produce more of these types of fuels, then we get a greater cost effectiveness associated with that carbon abatement. Okay. So in terms of these scenarios that we've analyzed, looking at some of the conclusions there, you can see that this RFS mandate should be met under these assumptions for domestic biofuels production with costs that would range somewhere between $3.40 and $5 per gallon, the gasoline equivalent. And that's at the refueling station. Also, you can, of course, see that these would cluster for the urban resources. These all show up at the urban centers, and that's partly based on the way we've allocated the sites in the model, the optimum sites. But of course, we do produce most of the municipal solid waste in the urban centers, but also the Corn Belt is then also the primary location for ethanol production from the agricultural residues, and then the woody resources in the southeast are producing most of the fuel supply there. And the national supply is sensitive to a number of things, of course. It's sensitive to the development of some low-cost cellulosic biofuel technology. And we don't yet have demonstrated such systems. There's a lot of research going on, but this is an area where we really need to develop capacity pretty soon if we're going to try to meet the standard within the time frame that the law provides. We also have issues associated with the acceptability of MSW resources, the urban resources, into biofuel conversion systems. They're not always the most homogeneous materials, and so there are issues around the use of this. We've just assumed that they are available, that some fraction of them are available to do this. This would be a concern if that fraction turns out not to be available to us. That's a fairly large amount of fuel that would come from the system as assumed here. And of course that we have access to the forest biomass and can get that out and use it. And of course the availability and yield of herbaceous materials from the marginal farmland is associated with the energy crop production in the model, and so the availability of resource from these lands is also a particular concern in trying to apply the results from this particular scenario analysis. Some of the other issues associated with the model, of course, this all is based on sort of the nth plant analysis. These costs, these techno-economic factors to really look at commercial facilities. We really need to look at the costs as we develop the industry out. The first cost, plant, and then moving on beyond that. The first cost will be substantially higher than these nth plant costs, and so that will affect the supply curve for the price levels that we've assumed. And of course, the industry cannot be built out overnight, so we're not going to put all of these places or all these facilities in these places immediately. We have to develop the industry over time, and that temporal aspect with the system has not been yet included. That's something we're looking to include in the future with the model. It's all very deterministic at this point, so we don't have a lot of uncertainty analysis associated with that, and that also is to be included in the future. And we haven't directly linked the impacts associated with this industry development with the costs. Okay, so we haven't as we build out this industry, as we produce more biofuel, as we affect the emissions and the like. This will all should have feedback on the costs associated with the conversion and delivery of these products. And we have used a fairly simplified model of the industry, and this, of course, the industry will be much more complex than what we've assumed in the model here, and there'll be much more competition potentially for different types of products coming from this resource. On the nth plant question, there's been some analysis, mostly by Nathan Parker, who's a postdoc working on the project, looking at how these nth plants costs might change as we go from our initial installations to the 10th and beyond plant. And you can see some analysis here. This actually comes from a paper by Annex. But you can see some range here as we look at what the current cost might be for different technologies, the biochem by dilute acid, some gasification processes, pyrolysis processes, and then what the nth plant estimates might be. So these are substantially below what the current cost might be for these types of technologies. And we have to better understand what those final costs might be for the industry and how long it'll take to get there. We also are looking at air quality impacts associated with this industry development. So as we build biorefineries, they will have local air quality impacts. They do have emissions associated with them. If, for example, we're going to build facilities in non-attainment areas for air quality, what impact does that have on the industry siting? Would that cause, for example, would the requirements to control emissions and the costs associated with that, would that require, or would that motivate the industry to move that facility someplace else? And perhaps with using some other resource or increasing transportation costs. And so we're right now in the process of trying to generate that effect within the model as well. We can also compare different products. For example, if we look at biofuels versus electricity from the resource, we've done some analysis of this for California. You can see something about, if we look at the biofuel price down here, and then compare what the electricity price would be to motivate a resource to electric power generation, keeping in mind that we do have at present about 500 megawatts of electricity generation from biomass in the state right now. And you can see what effect this has. So, in fact, in these types of analyses where the biofuel has prices or commands an economic value close to gasoline, then electricity is not necessarily the preferred conversion technology. Okay? But then, of course, we may electrify more of the vehicle fleet, and we have to look at the impacts of that as well, and the efficiency of the system. And just to, I said I would finish up here, but we are trying to integrate other modeling approaches here. For example, a lot of this analysis has been done at fairly low resolution on the resource side, and we want to try to get better information at the farm level. And so Steve Kafka and Mark Jenner, Steve is an extension agronomist at UC Davis, working with the economist Mark Jenner. They have been working on the development of something called the bioenergy crop adoption model, in which they're looking at the farm scale, trying to understand, at least for California in particular, how energy crops might come into the system. Under what conditions would energy crops come into the system? And so they've developed another model looking at the optimization for the farm based on various prices associated with these types of energy crops in relation to agricultural crops. And then they've come up with various estimates. For example, if we look at, in this case, an increase of $20 per acre profit, what energy crops might come in different locations within the state. And you can see this is Northern California here, Central California, Southern San Joaquin Valley, and Southern California. You can see that there are some changes within the cropping patterns associated with energy crops that might come in for these selected energy crops. You can see, for example, here in Central California, there might be something like a 4% increase in sugar beet production for alcohol production as the profit associated with that sugar beet production increases, in this case by $20 per acre. So just in general, these geospatial models and optimization, the geospatial optimization modeling really adds a lot of assessment capability in terms of trying to understand how this industry can make the transition, how we can produce this transition to much more bioenergy, how we can better understand the policies around this, the influence of the policies, and how we can better understand the economic performance of the industry and how we might adapt that and design for different policies. These supply outcomes are, of course, dependent on coupling these feedstock with the end products. And so the farm gate prices for the biomass will vary spatially as we site these facilities. And of course, as there are higher transport costs in relation to where that biomass is produced. And of course, we're looking at further extensions of the model to enable more temporal analysis so that we can build out the industry and look at the effects of that, as opposed to assuming simply an industry put in place at any particular point in time. And so we also want to be able to use that to do more comprehensive environmental assessment, especially associated with local impacts, local air quality impacts, water quality impacts, and the like, in addition to the greenhouse gas impacts associated with that. So I think that's it. I'll stop there. And sorry for running over. If there are any questions, I'd be happy to address them. Thank you very much. Carl, you had a
question? We have questions right in front here.
Carl Brown, CIE. First, what is your definition of a pioneer or pilot plant? And second, I'm California-centric, so why doesn't ag waste show up in the Central Valley?
Yeah, why doesn't ag waste show up in Central Valley? Yeah. So on a pioneer plant, so these first plants that are built, you know, we have the assumptions that you're looking at here are really for more of an nth plant assumption. So for a pilot plant basis, if we go back to, for example, this slide here on, which came from the Iowa assessment, the costs associated with these are somewhere in this vicinity here. And so if we look at a pilot plant, and we have a few pilot plants that are in development, and but they typically are in the range for biofuel production somewhere in the neighborhood of 1 million gallons per year that we're looking at for those.
What is a pilot plant?
Oh, okay. What's a pilot plant? Yeah, so a pilot plant in my definition would be the scale from laboratory. We would move through pilot phase, and that could be a variable capacity. In fact, typically on the order of, most of the pilot plants that I'm familiar with are typically on the order of 4 to 10 tons per day. That might be a pilot plant. But we can have pilot plants that are much bigger than that as well. So as we move to commercial capacity, if we're looking at facilities with these new technologies that are in the 50 to 100 million gallon per year range, perhaps, we might look at pilot plants that are in the 10 million gallon per year range as a step forward to advance that technology to full commercial scale.
So are any of the 500 megawatts in California pilot plant scale, or are they all increments?
Yeah, well, see, there again, we get into the question of what constitutes the pilot plant. Is it a question of time in development as well as size, which I would say it is. But we have power plants that range in capacity typically from about 5 megawatts on up to 50 megawatts. Again, we don't get above 50 megawatts for the biomass fueled power plants in California because of this licensing review by the California Energy Commission. Right? So we're limited in terms of the power plant size by that review typically. We could potentially go higher in capacity than 50 megawatts, but again, the cost of doing that is basically associated with the permitting around that facility. I don't know if I answered your question, but I would say that those facilities are commercial because they've been in operation for a length of time that would suggest that they are commercial.
Okay, we have any questions?
You mentioned a relationship between plant size and risk associated with, I believe, transportation of feedstock to the plant. Could you say anything about what typical assumptions are made about the relationship between size and risk?
Okay, in this model, because there is no risk assumption, so we don't account for risk in this particular model. That is something we're looking to include as we do more uncertainty analysis. In this particular case, all we do is run the cost model, the transportation cost model within the network that feeds the biorefineries for these various sites. So there's no inherent risk analysis within the model at present. The example that I gave around the scale factor, the common assumption has been that we just use some fixed scale factor to do the optimization, then we wind up with these very large facility sizes. But I think there's an inherent risk associated with going to these very large sizes where we have a distributed feedstock that has to be transported into that facility. So that was the issue there.
I think that's it. Thank you very much, Bryan.
All right, thanks very much.